Hello, Mr. Kramer here, talking to his integrated chemistry and physics group. We are going to do the standardized practice test with this video. So if you could open your chapter books to page 579 or 578 and 579, we'll find the standardized practice test that we can then do together. We have, over the last couple of weeks, been talking about, of course, chemistry, talking about the structure of the atom. We've been talking about the fact that electrons are what are shared or stolen from a neighboring atom to create ionic or covalent bonds. And this chapter is called Chemical Bonding, chapter 18 in our textbook. You guys have done an outline for me on chapter 18, and I greatly appreciate that. If you haven't done it yet, feel free to turn it in. As a matter of fact, don't let just because May 8th comes and goes, you can still do it for another week or two, and I'll include it in your quarter 4 grade, okay? I'm not in a big hurry for it, but I mean, obviously we are going to come to some sort of a real deadline. So just give yourself the gumption to get her done sooner rather than later would be my hope. Okay. Yesterday I did a drumming kind of bell ringer for us all, so I won't do a bell ringer today. It really doesn't require you to do anything except watch it. Let me know what you think. I enjoyed playing the knack song called My Sharona on the drum set, just to kind of give you a little bit of a boost in the arm, a real bell ringer, something that hits you upside the head, right? And I of course replaced the word Sharona with Corona, and that joke's probably getting old by now, thank God. Now there is a lot that we need to be thankful for. We need to be thankful for the fact that God made us in His image and likeness. We are unfathomably precious, each one of us. We need to be thankful for God doing everything. All glory be to God. There is nothing that we have that He has not given to us. And what we ought to do, given that fact, is the only proper and just thing to do is for us to give it all back to Him. Back to God, back to Jesus, back to the Father, back to the Holy Spirit. Give our all back to God. And I know the reasoning, I know the logic, I know the mathematics behind all of that. There's everything we have was given to us by Him. Our mother, our father, our car, our gym clothes, literally everything that we have, He gave us. And so it is for us to use and not abuse. It is for us to use for His glory, and thus we give it all back to Him. Every bit of it. We give everything back to God. And Lord, help me to live that way right now while I go through this standardized practice test with my students, and help my students to do work in the same way, to work on this standardized practice test to increase their understanding of chemistry so that they can give all of it back to you. In your mighty name, Jesus, amen. Thanks, everybody, for praying with me. So the standardized test practice, chapter 18. Long time coming. I hope you guys have been doing well academically in all of your classes, and I would encourage you to do so. Continue that until you're done. Do it. It won't hurt you. Nobody can take knowledge away from you. And we all need knowledge. Okay. So on page 578, question number 1. Goes like this. Which element is not part of the compound NH4NO3? Okay? Which element is not part of the compound NH4NO3? Okay? So we're given 4 choices to choose from. Well, let's answer a different question. Let's flip that around. Let's not even look at the solution yet. Let's look at what elements are part of the compound NH4NO3. That's ammonium nitrate, it's called. Ammonium is a multi-atom ion. Ammonium, NH4, okay? And then, and that's 1, so there you could put a bracket around it because it's an ion. You could put a 1 there if you wanted to, but that's redundant. And then the other one is NO3, okay? Ammonium nitrate. This has an oxidation number of +1. This has an oxidation number of -1. So you have 1 of each. This is what's called a complex ion. All right, so what's in ammonium? Well, we have nitrogen, right? So that N stands for nitrogen. If you look up the N block on the periodic table, you'll see that it is called nitrogen. And then hydrogen. If you find the H block in the far upper left of the periodic table, you'll know that it's called hydrogen, if you don't already know that off the top of your head. All right? Here, in this complex ion, which is a complex that has a -1, so this is an ionic bond, you would expect. You would expect ammonium nitrate to dissolve in water, and it does. Ammonium nitrate, if you'll recognize, is a fertilizer. It puts nitrogen in the ground. You spread ammonium nitrate out on the ground, it comes in white, opaque pellets. You spread ammonium nitrate on the ground and the corn grows like crazy. Soybeans grow like crazy. They need a little bit of nitrogen in the soil down at the roots in order to grow as fast as they can. I mean, it's good to put fertilizer down on the ground. Okay, so nitrogen, hydrogen, here's another nitrogen, so I won't write that one a second time, and oxygen. All right? So ammonium nitrate has nitrogen, hydrogen, and oxygen in it. Now, the question was, what isn't included in ammonium nitrate? Now let's go to those solutions. Nitrogen is included, oxygen is included, nickel is not included, hydrogen is included. So B, nickel, number 1, is B, nickel, right? Nickel is not included here. There is no nickel element, and I believe that's Ni if I'm not mistaken, and that's a metal. Might even be a transition metal. Let me look. Nickel. There it is, right next to copper. Remember, cobalt, nickel, and copper are the triad, or is that the coinage? No, that's the iron triad. I'm sorry, iron, cobalt, and nickel are part of the iron triad in the transition elements, right? That was from our last chapter. Okay, so aside from hydrogen, this is number 2 now on page 578. Number 2 is, aside from hydrogen and helium, when an atom is chemically stable, how many electrons are in its outer energy level? Okay, so helium is stable. It has 2 electrons in its outer energy level, but its outer energy level is full. So that's periodic table row number 1. But what about periodic table row number 2? How many electrons are in the outer energy level that is full of the second row on the periodic table? Well, it's not 0, it's not 4, it's not 7, it's 8. 8 electrons. It's called the rule of 8. You have a stable element. All those noble gases on the far right side of the periodic table, I've got them right here. Remember your back flap? Put your finger in there so you can get back there real quick. But these elements right here, these are called the noble gases. They don't react. They're very stable. They just bounce off other atoms. They simply are not interested in grabbing an electron or giving up an electron to another atom. Not reasonable for them. They're just too happy the way they are. They're in love with themselves. So, 8, D8, okay? Use the figure below to answer questions 3 and 4. So, number 3, what type of bond holds the atoms in this molecule together? So what do you have here? You have hydrogen and fluorine, okay? H and F. So you look those up on the periodic table, and what do you see? You see F is over here. F is one of those halogens, okay? It is very much wants an electron, so it can become like neon. It wants to become like neon. And hydrogen's way over here on the left. So hydrogen and fluorine are going to make an ionic bond, okay? And it will dissociate in water. If you put hydrogen fluoride crystals in water, they will dissolve, and they'll become H+ ions and F- ions, because the electron from the hydrogen will be stolen over into the fluorine atom, okay? And the hydrogen will be happier as a H+ ion floating around in water, and fluorine will be happier floating around as a F- ion floating around in water. Okay? So 3, what type of bond holds the atoms of this molecule together? Well, that would be an ionic bond. Okay? B. Answer B. Okay? Which statement about this molecule is true? All right? So, A, this is a nonpolar molecule. B, the electrons are shared equally in the bonds of this molecule. Not true. It's also not true that it's not a nonpolar molecule. This molecule does not have oppositely charged ends. That's not true either. This molecule does have oppositely charged ends. The center of positive charge is over there in the hydrogen atom, and the center of negative charge is over there in the fluorine atom. This is a polar molecule. Ah, there it is, D, the only true answer here under number 4. D, this is a polar molecule. And it's polar because it's an ionic bond, right? If it were more of the more covalent, like when you have oxygen doubly bonded to another oxygen atom, that's called a diatomic element or molecule, and each oxygen pulls equally on the shared electrons. So that one is truly not a bipolar molecule. But the further away you get from being equal shares of electrons, the further away you get from being a bipolar molecule, okay? Look at H2O. We've talked about that many times. Hydrogen is, both hydrogens are slightly positively charged, and the oxygen element atom is slightly negatively charged because it wants the electrons from the 2 hydrogen atoms more than the hydrogen atoms want those electrons. Okay, so there's a separation of the center of positive charge and the separation of the center of negative charge from those two. So the positive charge center is in between the 2 hydrogen atoms on a water molecule, and the center of negative charge is in the center of the oxygen atom. And so the positive and the negative centers of charge are not in the same place. That's called a bipolar molecule, okay? So when you have an oxygen attached to an oxygen doubly bonded, the center of the negative and the center of the positive charge of that molecule is in exactly the same place. When you have hydrogen and fluorine, they're not exactly in the same place. As a matter of fact, as we've already discussed it. I won't repeat that. I love you guys. I'm glad you're moving along with me. Number 5 on page 578. What is the oxidation number of sodium in the compound Na3PO4? Okay. Sodium phosphate. All right. So phosphate is a complex ion. Just like this is a complex positive ion, that's a complex negative ion, and they are ionically bonded between the two of them, ammonium nitrate. Now we're talking about sodium phosphate. It's Na3PO4, okay? This is a phosphate ion. This has a -3 oxidation number, and sodium always has a +1 oxidation number. And that's why there's 3 of them. 3 sodiums and 1 phosphate ion. Okay? So this is a neutral molecule, and there are the phosphate ion has 3 sodiums attached to it. And they are all +1. And this guy here is -3. This guy's stealing electrons from the sodium metal. Notice sodium is in the first group. It's an alkali metal. Right. Alkali metal is the name of the first group on the periodic table. Let's look that up for you real quick. So there's sodium right there. Okay? It's in group 1. And it gives up an electron readily. As you know, it'll even react with water. So sodium, these are 3 ionic bonds surrounding this phosphate molecule complex. Okay? And so, sodium phosphate. Oxidation number of sodium in the compound. So what is the oxidation number of sodium? I said it. It's +1. The sodium always has an oxidation number of +1 in all of its molecular formulations. It never has an oxidation number of +2 or 0. It is always an oxidation number of +1. Some of the transition elements have more than one possible oxidation number. Okay? So, there we go. Number 6, excuse me. Which element is least likely to form an ionic bond with sodium? Which element is least likely to form an ionic bond with sodium? Okay, so you got phosphorus, you got silicon, you got chlorine, and you got argon. All right, now argon, I believe, is a noble gas. Right here. Argon is it has a full outer energy level. It has 8 electrons in its outer energy level. It's not going to react with anything, okay? So argon is the least likely, but let's look up the other 3 to prove that with ourselves. Chlorine. And what are we reacting it with? Sodium. All right, sodium chloride. You've all seen sodium chloride dissolve in water. That's table salt. Chlorine is right here, next to argon, okay? Chlorine is so likely to form an ionic bond with sodium, it's amazing. I mean, there's fire and explosions that happen as sodium and chlorine come in contact with each other, okay? The chlorine atom wants an electron really badly, and sodium doesn't want an electron really badly, and so bam. All right, so sulfur. Sulfur is right here next to chlorine. Here's argon, chlorine, sulfur. Sulfur is likely to form an ionic bond with hydrogen. It's going to be H2S though, because sulfur wants 2 electrons. Hydrogen has 1 electron. So it's going to be H2S. You've heard of that. It stinks really, really bad. It's one of those real smelly gases that cause you to run. It's so bad. Okay, and then what's the other element called? Phosphorus. So they're talking about these 4 elements right here in this question. They took these 4 elements out here. Phosphorus is least likely to react with hydrogen of those 4 elements. okay, it wants 3 electrons to get to a full outer energy level. So H3P would be the simplest molecule you could make with phosphorus. Here, you'll notice you've got sodium phosphate, which phosphite and phosphate, and there's phosphorus is normally linked to oxygen and makes these complex ions, and then hydrogen like would be an H3PO4 instead of a Na3PO4, right? Because hydrogen and sodium are in the same group. Anyway, just pointing it out. Number 6. So number 6, the answer is D, argon. Argon already has 8 electrons in its outer energy level, and it has no desire to react with anything, let alone a hydrogen atom. Okay, right? Number 7. How many electrons are required to complete the outer energy level of a phosphorus atom? Okay, well, to get all the way over to the column with argon in it, you have to add 3 electrons. So the right answer is 3, C, 3. It needs 3 electrons to complete the outer energy level of a phosphorus atom. Okay? All right, number 8. How many electrons are in an argon atom? Okay? You can count them right there if you want to count each little electron, right? There's 8 in the outer energy level, there's 8 in the second level, and there's 2 in the first level. So 2 plus 8 plus 8 is 16, right? Everybody follow that? No, that's 18. Sorry. 2 plus 8 plus 8 is 18. Not 16. Okay, so we got 18 as an answer. C. How many electrons are in an argon atom? 18 electrons. The atomic number of argon, guess what? It's 18. There are 18 protons in an argon nuclei of the atom. And then you can also, you guys know how to figure out how many neutrons there are. You subtract the atomic weight minus the number of protons, and you get the number of neutrons, right? Okay. What do the group 17 elements become when they react with group 1 elements? Okay, so group 17 are halogens, right? And they react readily with group 1 or alkali elements. These group 1 elements and these group 17 elements are highly reactive. These make ionic bonds. When you're this far over on the left and that far over on the right, you make an ionic bond. Now, of course, this one is the exception. It does not react at all. This is the most reactive. This is the most reactive column on the periodic table, and they make ionic bonds. And so what does this column become? Does it become positive or negative? Well, it takes the electron from group 1 elements, right? Because they want to get rid of an electron. It takes the electron. What charge are electrons? They're negative charged. So if it takes an electron from a neighboring atom, then it becomes a negative charge. It has one more electron than it has protons. And so they become negatively charged, which I think I saw that as an answer. A. 9 answer is A, negative ions, right? The group 1 element becomes a positive ion. They're not neutral unless there's a covalent bond involved. And it's not a polyatomic ion because it's just that atom from group 17, right? What do group 17 elements become when they react with group 1 elements? They become negative ions in water. Okay. What is the name of potassium C2H3O2. I bet that's a polyatomic ion. C2H3O2. I can't remember what that is, but I kind of recognize it as a polyatomic ion. I think what we have here is a K plus 1 and a C2H3O2 minus 1. Okay? So I'm going to look up the name of that. I'm going to look up the name of that complex ion. It's in our chapter. Okay? If you guys can beat me, that's great. Please do. I'm looking for a table that has that polyatomic ion on it. There it is, acetate ion. It's on page 569. There's a table on page 569. Okay? And it's the acetate ion. C2H3O2, acetate ion. Okay? Sorry I didn't remember that off the top of my head. Okay, so potassium acetate is the name. Potassium acetate. Okay? And that is B, answer B. Okay, everybody follow that? Number 10 is answer B. Number 11, how many electrons are in the outer energy level of a helium atom? How many electrons are in the outer energy level of a helium atom? Okay, let's look at the periodic table for help. A helium atom is right there. Okay, 1, 2. 2 electrons in the outer energy level, and it's full because it's level 1. Level 1 only has 2 electrons. Okay? So the answer to number 11 is B, 2. How many electrons are in the outer energy level of a helium atom? 2. If you were in a Jeopardy contest and the answer is 2, you could say, how many electrons are in the outer energy level of a helium atom? Buzz in, right? Okay. I think we're getting there. I love you guys. All right, so 12. We're ready to move on. Look at this graph here on the page. You got neon, fluorine, oxygen, nitrogen. These are the oxidation numbers of these different elements on this table. This is more like a bar graph than a line graph, if you ask me, because they're talking about oxidation number, and if they had said neon down here, fluorine down here, oxygen down here, and nitrogen down there, it would have been a bar graph. But they've got nothing here on the x-axis. Okay? There you have it. I would never make this graph, okay? I would look at a periodic table and know what the oxidation numbers are for these elements, okay? Describe the trend in the oxidation numbers of these period 2 elements, okay? Number 12, describe the trend. Well, the oxidation numbers are decreasing if you organize it this way. But what if you put nitrogen first, and oxygen second, and fluorine third, and neon fourth? The oxidation numbers would be increasing, right? But this particular trend, there you say this is decreasing. What else can you say the way they've got it drawn up? Okay? I don't know that I don't know what they're trying to get at, other than maybe wanting you to know how to use the word decreasing. You see, in Jeopardy, when there's an answer decreasing, you could say it is a line graph of oxidation numbers for neon, fluorine, oxygen, and nitrogen. In that order. decreasing, right? Describe the trend in the oxidation numbers of these period 2 elements. Decreasing when you line them up in the order that they're given, okay? Notice there is an oxidation number of 0. It's the noble gases. They will never, the oxidation number of a noble gas is 0. It will not accept an electron, it will not give up an electron in a chemical reaction. Okay. Number 13. Why do the oxidation numbers of nitrogen and fluorine differ? Well, nitrogen is in a different group than fluorine. That's a perfect answer right there. Nitrogen is in a different group than fluorine. Okay? It needs 3 electrons to have a full outer energy level. Fluorine only needs 1 electron to have a full outer energy level. Are you following that? So, you could put down those 2 different answers. Both are completely perfect. Number 14, draw electron dot diagrams for carbon and hydrogen. Draw a dot diagram for methane, one of many compounds formed by these 2 elements. Okay, so hydrocarbons have electron dot diagrams, and carbon and hydrogen have electron dot diagrams. Let's do those. We'll do them right over here on this, in this area right here, okay? So here's an electron dot diagram for carbon. Carbon is an element on the periodic table, and it needs 4 electrons. Carbon has 4 electrons in its outer energy level, okay? 1, 2, 3, 4. It's in this group right here. 4 electrons in its outer energy level. You can tell that by looking at the periodic table, okay? And those are often drawn like this. And carbon ends up not filling up the 2 orbitals available in the 1s orbital. Carbon often sends an electron out here. There's 1 in the 1s orbitals, and there's 3 in the 3p orbitals. This is a more stable electron configuration than this, where you have a full energy first energy level and 2 electrons in the second energy level. I'm sorry, this is the outer energy level. This is always this outer energy level. Forgive me. I pretend I didn't just say what I just said. Don't worry about it. Oh, sometimes I get things goofed up. I know too much, and I get things goofed up and in my head, and then when it comes out, and I fail to explain things correctly. Carbon's outer energy level electrons, there is 1, 2, 3, 4, and carbon often reacts with 4 things. Here's a hydrogen electron dot diagram, right? Okay? And now methane, CH4. So this is carbon element. This is hydrogen. All right? And now let's hydrogen actually never exists like this in nature. It always exists with as an H2. Hydrogen is an H2 molecule. It's always a diatomic molecule. If you have a jar of hydrogen, you always have hydrogen bound to a second hydrogen atom, okay? It's a diatomic molecule. Okay, so here's carbon, here's hydrogen, and CH4 now, methane. Methane, CH4. That's a carbon with its 4 electrons, and then 4 hydrogens. Bam, 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 bam. Hydrogen, 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 hydrogen. Okay? So that is the electron dot diagram for methane. Okay? Is there another question here? All right, that's it. Number 15. Give several examples of ionic compounds. What are two properties often shared by these compounds? Okay? So give several examples of ionic compounds. All right? Well, we know ionic compounds form when a group 1 and a group and a halogen, a group 1 alkali metal and a group 17 halogen, when they react, they form ionic bonds. So here we go. So we got hydrogen fluoride, right? We've got, so this is, let's call this one the fluoride ionic bonds. And then there's the next one down after fluorine is chlorine. Chlorine, bromine, and iodine. And then there's one more, I can't remember the name of it. It's kind of rare in nature. It's called astatine. Okay? And here is hydrogen. This is the group 1 elements. Hydrogen followed by, I think, lithium. And sodium. And potassium. And rubidium. And cesium. And francium. Okay? So these guys are, so this is HF, LIF, NaF, potassium, fluoride, rubidium. Is that a RU or a RB? Rubidium. RB. RB, F, rubidium fluoride, cesium fluoride, francium. I think it's just a capital F. Let's make sure. Nope, FR. FR. F. I guess if it was just an F, that would be fluorine. Okay? So these are all ionic bonds, right? This is the group 1 elements and the group 17 elements. Here we go. What do we got? Now, here's HCl. You guys have heard of hydrochloric acid, I'm sure. Lithium chloride is a salt. Sodium chloride is a salt. Potassium chloride, that's in salt. Rubidium chloride. Cesium chloride. Francium chloride, right? Here's bromine. Hydrobromic acid. Lithium bromide. That's a salt. Sodium bromide. Another salt. Potassium bromide. Rubidium bromide. Cesium bromide. Francium bromide. Okay? So these are all salt. Here's now we've got the iodide salts. Hydrogen iodide. That's considered when you have a hydrogen on the front of one of these, it's called an acid. Lithium iodide. sodium iodide, potassium, I'm sorry, not potassium, potassium iodide, rubidium iodide, cesium iodide, francium iodide. And this is astatine. So this is hydrogen astatide, lithium astatide. Is it AS or is it just A? AT. Lithium astatide, sodium astatide, potassium astatide, rubidium astatide, cesium astatide, francium astatide. Okay? So the question said, write down give several examples of ionic compounds. Well, we just gave 1, 2, 3, 4, 5, 6, 7 times 1, 2, 3, 4, 5. That's 35. I think that's enough. We gave 35 examples of ionic compounds. What are two properties often shared by these compounds? Okay. Two properties often shared by these compounds. One, they dissolve in water. They dissolve in water. Right? Two, something in common to each one of these is that they have an oxidation numbers of +1 and -1. Each one of these has a +1 and a -1 oxidation number. Okay? All right? You can have ions like calcium chloride that dissolve in water somewhat, right? Calcium is in group 2, so it would have 2 chlorine atoms attached to the calcium in order to make the oxidation number balance, right? So you'd have calcium chloride would be another example. I'll draw it over here. Calcium chloride, right? This has an oxidation number of +2. It's in group 2, and it wants to get rid of 2 electrons to have a full outer energy level. And chlorine wants 1 electron. So it has a -1, and there's 2 of them in order to make this oxidation count balance in the molecular formula. Okay? Calcium chloride. And that will become, that's somewhat dissolving in water, and what you end up with is a negative chlorine ion in water and a positive calcium chloride ion in water. And that'll also dissolve in water too. The positively charged calcium chloride complex ion will also dissociate in water. And you'll have a calcium 2+ and 2 chlorine- ions in water. Okay? Are we ready to move on? We gave several examples of ionic compounds. All right. This is an ionic compound. 2, sodium phosphate, potassium acetate. This is an ionic compound. Okay? And back over in question number 1, ammonium nitrate. That's an ionic compound as well, where you have ammonium with an oxidation number of +1 and a nitrate with an oxidation number of -1. Those two will dissociate in water and float around as complex ions. Okay? Number 16 on page 579. A compound has the formula magnesium sulfate, .7H2O. So that means it's a hydrate. It's a molecule with H2O incorporated into the molecule because it does that. Magnesium sulfate allows water molecules to come and hang on, glob on, and it's more stable in that form when there's water around than as magnesium sulfate crystals. Okay. Identify and define this type of compound. Well, I'm remembering it's, the word hydrate is used in the name of the compound. Compounds with added water. A hydrate is a compound that has water chemically attached to its atoms and written into its chemical formula. Okay, so those are called hydrates. So the first part of question number 16 on page 578 is, it's a hydrate. Using the appropriate prefix, write its name. Okay? So, I'm going to erase this right here and do it right here. Okay? Magnesium sulfate. Magnesium is a +2, sulfate is a -2, dot 7H2O. Okay? So I can't remember what the prefix is for 7. I think that that's given in our book back here. 7 is has a prefix. There it is, hepta. Okay? Heptahydrate. So this is called magnesium, and you could look up this word on your periodic table for Mg, magnesium sulfate heptahydrate. Boy, what a big word. Magnesium sulfate heptahydrate. Okay? Have you seen that laundry detergent commercial where that guy's spinning around inside a circular front window washing machine? It's got some soap on his forehead or whatever. He's spinning around inside the washing machine, and he says, "This laundry detergent has blah 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 blah." Yeah, I don't know what that is either, he says. Okay? I'm going to have to write that one down and see if I can figure out what the molecular formula is. This is magnesium sulfate heptahydrate. I actually think that commercial's funny. I like that commercial. Okay? Where am I at? So now I need to go back to, by the way, that hepta prefix for the number 7 was found on a table on page 570, if you're interested. Okay? You ought to go back and take a look at that. So you know that these prefixes are defined. Number 17. What information is given in a chemical formula? Okay? What information is given in a chemical formula? The number of elements, the number of atoms. These are 2 atoms, right? This is 3 atoms. So the number of atoms and the type of atom, the exact type of atom, is also given in a chemical formula. Okay? As well as you can infer the oxidation number of an element. When you have calcium chloride, CaCl2, and you know chlorine is always a -1, you can infer the oxidation number of +2, which happens to be correct also because it's in group 2 of the periodic table. It gives up 2 electrons. Chlorine takes 1 electron because of where it's at on the periodic table. You can determine that. Okay? So the chemical formula with a periodic table lets you know what the oxidation of the atoms are, oxidation numbers of the atoms are. Right? Okay. Let's keep moving. Number 18. Describe the bond holding the atoms together in this molecule. So this is an N2 molecule, okay? And what you have is nitrogen triply bonded to the other nitrogen, okay? The electrons in the outer energy level of nitrogen, nitrogen wants 3 electrons to have a full outer energy level. Nitrogen's right here on the periodic table, 1, 2, 3. It wants 3 electrons. So it will share 3 electrons with another nitrogen atom. And that's called a diatomic molecule. And that's the nitrogen that we breathe. We have 71% nitrogen in our atmosphere, N2. Right? It's a diatomic molecule. 71% of our atmosphere is nitrogen, N2. Okay? So describe the bond holding the atoms together in this molecule. It's a covalent bond, and it's a triple bond. So it's a covalent triple bond in N2 molecules. Okay? That's the answer to number 18, a covalent triple bond. Number 19. Nitrogen occurs naturally as a diatomic molecule because N2 molecules are more stable than nitrogen atoms. Hydrogen, H2, also a diatomic molecule. Oxygen, O2, also a diatomic molecule. Fluorine, F2, also a diatomic molecule. If there's nothing else for it to react with, if there's just a jar of fluorine gas, it's going to be a jar of F2 because it really wants to have a full outer energy level. Same with chlorine, same with bromine, same with iodine. I'm reading question number 19 on page 579. Are other diatomic molecules? Draw dot diagrams for 3 of these molecules. All right? Let's do dot diagrams for all 6 of them. We've already got dot diagram for hydrogen right here. You can't see it. There's hydrogen dot diagram right there. H2. Are you ready? What about O2? Well, oxygen needs 2 electrons to have a full outer energy level. So I'll do it right here. Oxygen is going to share 2 electrons with another oxygen atom. It's going to be doubly bonded. So this is a double covalent bond. Oxygen. So we've got hydrogen, oxygen. What's the next one? Fluorine. All right, fluorine. Now all of these are going to be the same. There's going to be 7 dots in that fluorine and 7 dots in this fluorine. 1, 2, 3, 4, 5, 6, 7. And fluorine, and this fluorine atom is going to share this fluorine's electron, and this fluorine's atom is going to share this fluorine's electron. And now they both have 8 electrons in their outer energy level. Very good. What about chlorine? Let's do chlorine. 1, 2, 3, 4, 5, 6, 7. Chlorine. 1, 2, 3, 4, 5, 6, 7. So both chlorines have 7 electrons. It's just like fluorine, same group. Its chemical reactivity is very similar to fluorine and chlorine because they're both in the same group, right? They're both halogens. What else have we got? bromine and iodine, two more. They're going to look just like this. There's going to be a bromine and a bromine. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Bromine, and what was the last one? Iodine? I think so. Yeah, I2. I and I. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That makes it happy. Makes the iodine happy when it runs around paired up with itself. These are all diatomic molecules. They're all diatomic molecules. Okay. Next. Explain why elements in group 4, which have 4 electrons in the outer energy level, are unlikely to lose all of the electrons in the outer energy level. Number 20. Explain why group 4 are unlikely to lose all 4. Bam, 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 bam. Why are they unlikely to lose all 4? Can you see that better when I hold it like that? Here's group 4. They said group 4. 1, 2, 3, 4. Everybody understand how that? 1, 2, 3, 4. That's how they got group 4. This periodic table calls them group 14. Other periodic tables call them group 4. We've talked about that more than once now. Okay, so they're not likely to use all 4 of their electrons. Why not? Well, once they lose 1 electron, okay, like let's say carbon tetrachloride, right? These are covalent bonds. These electrons on carbon are going to form covalent bonds with halogens, or even hydrogen. Let's put 1 hydrogen here. This is I'm going to put another chlorine here because I don't want to cause confusion about naming. This is called carbon tetrachloride. That's a molecule. It's very stable. Carbon tetrachloride, okay? And it's no longer a carbon element. This is called carbon tetrachloride. All right? And of course, chlorine has 8 dots around each one. I forgot that. There's an electron dot diagram for carbon tetrachloride. Okay? So why aren't group 4 atoms likely to lose all 4 electrons? It's because they're more likely to form covalent bonds than they are ionic bonds. Because when you're in group 4, the atoms that are not so far away are from an electromagnetic point of view, they don't grab the electron away. If you're over here in group 1, the halogens will grab the electron away. But if you're way over here in a column that has, it's mostly non-metal, when you have a non-metal and a non-metal reacting, they're not so different, right? So they're going to form covalent bonds instead of ionic bonds. That's the best answer I can come up with for that question. And I think that was number 20. Explain why elements in group 4, which have 4 electrons in the outer energy level, are unlikely to lose all of the electrons in the outer energy level. They're not likely to lose an electron, lose an electron, lose an electron. A carbon atom is not likely to lose 1, 2, 3, 4 and become more like a helium electron cloud, right? It's just either direction. These guys These guys, these green ones, sometimes act like nonmetals and sometimes they act like metals, right? But they're not likely to lose all 4 electrons. They start acting like nonmetals and they want to get an electron. Okay? So, what factors affect how strong? I'm on number 21 now on page 579. 21. What factors affect how strongly an atom is attracted to its electrons? Well, how close is it to having a full outer energy level? Does it need to lose an electron or lose 2 electrons or lose 3 electrons to get a full outer energy level? Does it need to gain an electron to get a full outer energy level? Right? So those factors are, what factors affect how strongly an atom is attracted to its electrons? If it wants to give up an electron to get a full outer energy level, it's not very attracted to that electron, right? If it wants to get an electron to get a full outer energy level, it's way more attracted to its outer energy level electrons, right? So it depends on how many electrons are in the outer energy level and how stable it is, or how close it is to having a stable outer energy level of 8 electrons, or full outer energy level in the case of helium. Okay? Number 22. Create a chart that compares the properties of polar and nonpolar molecules. Your chart should include several examples of each type of molecule. Polar and nonpolar molecules, okay? So all of these diatomic atoms are nonpolar, completely nonpolar, perfectly nonpolar, okay? Polar molecules are molecules made of different atoms. H2O is a polar molecule, okay? All of these are polar molecules right here. They're all polar molecules, okay? So we've given you lots of examples of those. Now a table. Create a chart that compares the properties of polar and nonpolar molecules. Your chart should include several examples of each type of molecule. I'm not gonna help you guys get that one done. As a matter of fact, I'm gonna make that a bonus question. Okay? If you guys want to do that one for a bonus, you go ahead. Number 22 on page 579. Number 23. What is the difference between nitrogen monoxide and dinitrogen pentoxide? Woo! Let's see. What is the difference between nitrogen monoxide and dinitrogen pentoxide? Okay. Here we go. I'm going to erase these diatomic molecules. What was it called again? Nitrogen monoxide. Nitrogen, okay, monoxide, oxygen. It wants to share. How does nitrogen make a double bond with oxygen? Now oxygen has 8 electrons. Nitrogen has 1, 2, 3, 4, but it needs a third. It needs a third. It has 1, 2. It looks like that. 1, 2, 3, 4, 5, 6, 7. It only has 7. Nitrogen monoxide. It must have another electron, and it's got a -1. This is a complex ion. This is a complex ion because nitrogen needs to react with another atom in order for it to be satisfied with 8 electrons in its outer energy level, or it might have an extra electron and this whole complex ion exists. So nitrogen monoxide is a complex ion. Okay? Now, dinitrogen pentoxide. Dinitrogen pentoxide. That's N2O5. Okay? So, lots of different ways nitrogen pentoxide can be combined with reactants, okay? Dinitrogen pentoxide. This has a nitrogen has a +3, right? Yeah. +3, oxygen has a -2. Okay? So +6 -10. I wonder if this is an ion with a -4. Could be. Let's check. Let's look in our books for dinitrogen pentoxide on that complex ion chart. All right, I'm not seeing dinitrogen pentoxide on this chart. All right. I'm thinking about using Google, but I'm going to make this one a bonus question as well, if you guys want to use Google to figure out what the differences are. I think dinitrogen pentoxide is an ion, and I think nitrogen monoxide is also an ion. I'm sure that is an ion, okay? But one of them is an ion with an oxidation number of -1, and the other one is an ion with an oxidation number of -4. That's my thought on that one. Now, I love you guys. We're done with this standardized practice test. I think there's probably one more thing I'm going to do with you. I'm going to do a lab, a virtual lab with you between now and the end of the week, and it'll be about chemicals, okay? We're going to do a virtual lab with chemicals. And I love you all very much, and there won't be an assignment except you're going to have to send me some sort of information that I gave you during that lab to tell me that you watched the lab, okay? And it has been my pleasure to be your ICP instructor this year. We learned a lot about physics. We learned a lot about electricity, which is part of physics. We learned a lot about stuff. A lot of integrated chemistry and physics was discussed this school year, and I'm proud of every one of you for your increased knowledge in the field of science. I appreciate your attentiveness. I appreciate your efforts. I love you. Thank you. God bless you.